Welcome back. This is the first of 3 lessons about a data structure called a binary search tree. This is a type of tree where the data is specially organized to make it easy for us to search for the information we want. In this lesson, you'll learn how to define a binary search tree and how data is added to a binary search tree, how we can use a binary search tree to find the data that we want, and we'll end up by creating a binary search tree from a series of data values. You've already learned what a tree is. Well, a binary search tree is a tree that's constructed in a particular way. There are rules about where each item of data must be stored in the tree. And that means by following those rules, we can find the data again. That is a much quicker way of storing and finding data than using a list or array. The rule for adding data to a binary search tree is very simple. You look at the root node of the tree and see what value is in there. If the value that you want to add is smaller, you go to the left, and if the value is bigger, you go to the right. Now remember that the tree is a recursive structure, so you can repeat this process as often as you need to until you get to an empty space. Adding data is a recursive process because each branch of a tree is itself a little tree. So you just keep repeating that. Go to the left, go to the right. I call it the left-right rule until we get to somewhere where there's an empty space and we can add the data. That might be very quickly or it might take ages, but we just keep following the rule until we get to an empty space. I've said bigger and littler. If the data values are numbers, then obviously we just use bigger or littler numbers. And if they are text strings of any kind, we use alphabetical order. There isn't a hard and fast rule about whether we're allowed duplicates or not. Some binary trees have duplicated values and some don't. We just follow the left-right rule in either case. Here's an example of a binary search tree. You can see it's a binary tree because none of the nodes have got more than 2 pointers. It's a binary search tree because the data has been added using the left-right rule. Now, supposing this is a typical exam question, supposing we needed to add the value 9 to the tree, where would we add it? Let's go through this process step by step. We look at the root node. 9 is bigger than the value at the root node, so we go to the right. It's smaller than 10, so we go to the left. There is no pointer at the left. That means there's space for a new value, and we add 9 there. Now if we want to find a value in the tree, we simply follow the same left-right rule, and that will take us straight to the data that we want in only a small number of operations, far fewer than searching through a linked list. So for example, how would we look for the value 4 in this binary search tree? Well, 4 is smaller than 8, so we go to the left. It's bigger than 3, so we go to the right. We're now at 6. 4 is smaller than 6, so we go to the left again, and there is 4. So following this rule, if a data value is in the tree, we should go straight to it by following this rule. But what if the value isn't in the tree? Let's look for the value 11, which you can quickly scan through and see it's not in the tree. But if we're a computer and we can only look at one value at a time, if these values were stored in a linked list, we'd have to go through the entire list to find that 11 isn't there, so n operations. But if we look for 11 in a binary search tree, it's much quicker to find that it isn't there. So obviously 11 is bigger than 8 and it's bigger than 10. It's smaller than 14, so we're following the route, and that takes us to 13, the node with 13 in it. We know 11 is smaller than 13, so it should be down to the left of 13, but there's nothing there. That's the end of the tree. Remembering the terminology, 13 is a leaf node. In any case, it doesn't have a left pointer. That's where 11 should be if it was in the tree. There's nothing there, so we know that 11 is not in the tree, and it's only taken 4 operations rather than n operations. Okay, now the order in which we add values to a tree will change the shape of the tree. Even though every tree obeys the left-right rule, the actual shape will differ. So here is an exercise. Make a tree from this list of data. So 50 will be the root node. Then you have to add 33, then 13, and so on in order. If you do that, there is only one right solution. So I want you to stop this video now and just on a bit of paper, you can do it scribbling by hand, it's fine. Create this tree from these values. And on the next slide, I'll show you what it looks like. This is the only way you're going to check if you've got it, is to try and do this before you look. So that's the answer. Compare that with what you've written down. If you haven't done it, go back a slide and try it and then come back and have a look. It should look exactly like that. If you investigate, you can see that every value there is added according to the left-right rule. This might be a good point for me to say that calling it the left-right rule, that's just what I call it. You won't see it called that generally, but it's just a nice easy way for me to remember what the rule for adding data is. I call it the left-right rule. You should end up with that table. Let's try again on the next slide. Here are the same values, but they're in a different order. The values are all between 1 and 100. I just picked them at random, but I've reorganized them here to be in a much less convenient order. So if you draw that tree, you'll see that it's not so well balanced, and it will take more steps to get to some of the values. Once you've done that work, if you've got time, think about how we can arrange values to make a well-balanced search tree. What helps the tree to be well-balanced? And is there an algorithm we can write to organize values into an order that produces an efficient search tree? This is quite a challenging task, and it goes beyond what is likely to come up in the exam. But those of you who are interested in data processing and higher maths might like to try to tackle that problem, perhaps even write a program to do it. Okay, in the next session, we'll look at answering exam questions about binary search trees. But bye for now.